Welcome everybody, good morning. I'm Charlene Varambourg from IS Global, so I'm a postdoc. I work a lot on the ELIX project for those of you who know this project, and today we are going to talk about some statistical challenges due to the exposome context, and we will do a small practice in R for those of you who want to play with some data. And for the other, you can just follow what I will do. Just before starting, if you want, or if you can, just turn on your video so I can just see your face and it's a bit more familiar, and then we can just turn off. And okay, I recognize some people. It's better like that. Good morning, everyone.
Good morning, Charlene.
Almost everybody working from home, I guess.
Good morning.
Good morning.
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 Hi, good morning.
Morning.
It's funny to see all your face. Okay, but maybe we should start. So I will change my screen, and so this, I guess you can see the presentation. And just before starting, since I'm sharing my screen, I cannot see the chat. So if you have some question, you can write them in the chat, and Amanda will manage them. So we will make some, thank you, Amanda. We will make some break during the presentation, so we will have time for questions. So this workshop is part of the Untitled General Assembly, and as I said, we will talk about statistical analysis to study exposome-health outcome association. So this presentation is divided in 4 parts, so a bit of background about statistical challenge and statistical methods available. Then we will talk about all the pre-processing we have to do to manage all this data. I will show you the main function of the rexposome package, and then we will make a small practice with R. So the first part, in environmental epidemiology, we were used to have a single exposure approach or a single family of exposure. And this has some issue because we can have some selective reporting of the association, which will lead to a publication bias. That means that we will mainly publish only the positive results, even if I also recommend you to publish the negative result, but the single exposure approach may lead to this selective reporting of association. And another issue is that by making one paper for each exposure, we will not take into account the issue of multiple testing. And another, and I think it's the main oh, I don't find the word. Anyway, the fact that we cannot take into account the co-exposure is also a limitation of the single exposure approach. So this is why we are moving now to an exposome approach, and also because we cannot consider mixture effect. So now the exposome approach calls for a holistic view of the effects of all or almost all environmental exposure on human health. But this exposome approach have some limitation or some challenges that we would like to overcome, including the dimension of data, because when we are dealing with thousands or not yet thousands, but hundreds of exposure, this leads two statistical challenges to study the association with an health outcome. Another important challenge is the correlation that may exist between exposure, and that can be very high, above 0.8, for example. The issue of multiple testing, missing data too, because as we increase the number of exposure of interest, we also decrease the number of individuals with complete case data. And at the end, the last, but I think this list is not exhaustive, but another challenge is the method that we would like to implement. We would like that this method can take into account interaction between exposure, which is also one of the aim of exposome study. So we can divide it, the approaches we perform in exposome study in two different parts. So the single exposure analysis. So the main methods that I think almost everybody knows is the ExWAS analysis on exposome-wide association study, which aim to estimate the exposure by exposure association and to correlate this for multiple testings. In that case, we will study each exposure in association with the health outcome, but independently of all the other exposures. And on the other hand, we have the multiple exposure approach that we can divide in two different components: the variable selection methods, which aim to identify a set of exposure that predict at best the outcome. So in that case, we will have exposure adjusted for other co-exposures. And we can also apply some clustering methods to identify some individuals that share similar exposure patterns. So this is a brief overview of statistical methods that are available to study exposome health association. So the ExWAS that I just talked about briefly, and then there exist a lot of different variable selection techniques. So I just put some of them that you may know, including the lasso, elastic net, the dilation, substitution, addition algorithm, the DSA, the SPLS, that can also be part of the data reduction methods, where we can also find the PLS, the PCA, and clustering methods, including hierarchical clustering. And all these methods can be also divided in another way. So between the supervised and the unsupervised method. So the supervised method means that you use your health outcome to build your model. So in all these methods, this will be the case. While in the unsupervised methods, you only consider the exposure. So for example, the PCA, you will make a principal component analysis on your exposure independently of your health outcome. We can add plenty of other methods. I made this selection for different reasons. The first one is that some methods, for example, the Bayesian kernel machine regression, that we can see a lot of new papers using these methods. I did not put it in this slide because in the exposome context, we have too many exposure to apply this kind of methods. I can also add, I don't know, neural network or structural equation modeling, and a lot of other methods. So in the ELIX project, what we have done first is to perform a simulation study to compare the performance of these different statistical methods in the exposome context. And this simulation study was based on a real correlation matrix from the INMA cohort and explore different scenarios, including a scenario where we expected 1 to 10 and 25 true predictors among more than 200 exposures. And the main conclusion of this simulation study is that the ExWAS analysis show very good sensitivity to detect the true association between exposure and the health outcome, but also a very high false discovery rate. And on the opposite, other selection technique, such as the DSA, the SPLS, or the elastic net method, show a lower sensitivity, a lower false discovery rate, but also a lower sensitivity, but still acceptable because above 0.6. So I have to say that this simulation study did not consider interaction between exposure nor nonlinear association. And this simulation study led to the determination of the statistical protocol in ELIX. And I will just give you a small example of an analysis that was done in ELIX. And since I don't know how many of you are familiar with ELIX and athletes, I will just give you a brief summary of this project. So the ELIX project is a human early life exposome project, and it enrolled 6 European mother child cohorts and perform a follow-up, a standardized follow-up of the children at around 6 to 11 years old, and characterize a wide number of exposure either during pregnancy and childhood. So here, the example I'm given is about data collected in 4 out of the 6 European mother-child cohort enrolled in ELIX. And the aim of this study was to explore the association between multiple exposure to human exposome during pregnancy and childhood, and its association with blood pressure measure at 4 to 5 years old. So this study includes more than 100 exposure, including air pollution, the built environment, traffic and noise exposure, meteorology, natural spaces, and socioeconomic status at the area level. And following the ELIX statistical protocol and the simulation study I just presented, we use 3 complementary approaches to explore the association between all these urban exposure and the blood pressure, so including an ExWAS analysis with 150 exposure, a variable selection technique, so the DSA algorithm, where we exclude from the original set of exposure the exposure that were correlated at more than 0.8 with another exposure. And at the end, I also perform, I still have issue to pronounce this word, hierarchical clustering following a principal component analysis. And this was done in using 50 exposure, so only the continuous variables. So briefly, what we observed that using the ExWAS, we observed that higher exposure to air pollution during childhood was associated with higher blood pressure at 4 to 5 years old, while at the opposite, we observed that higher temperature, for example, at the time of the blood pressure assessment, was negatively associated with blood pressure. So you can see that we have 2 different thresholds, the threshold usually used in environmental epidemiology or in statistics in general of a p-value of 0.05. And if we interpret the study using this threshold, we can also add some other association, including a lower blood pressure in association with green spaces or higher blood pressure in association with noise and some built environment variables. But as I said, with the ExWAS approach, we are at risk of false positive results. So this is why we apply a correction to limit this false discovery rate. So after correction, after p-value correction, only this association with temperature and air pollution remains statistically significant. So these are the results for the postnatal exposure in association with diastolic blood pressure. And if you want to see all the results, you can check the reference. So then we apply the a variable selection technique, so the dilation, substitution, addition algorithm among 67 exposure assessed either during pregnancy or childhood. And these techniques selected 5 environmental exposure, so either during pregnancy or during childhood. And the results are concordant with the result from the ExWAS. So we still observe a decreased blood pressure in association with higher temperature at the time of the blood pressure assessment. Also higher blood pressure with both exposure during pregnancy or childhood to air pollution. Higher blood pressure in association with higher exposure to noise. So even if we don't really see a clear dose response trend. And finally, also an association between higher temperature during pregnancy and higher blood pressure at 4 to 5 years old. And all these analyses were adjusted for a set of covariates as the ExWAS. And finally, these are the result of the hierarchical clustering performance principle component. So here you can see that with this method, we obtain 6 different clusters. So the individuals, so the children, were classified in one of those clusters. So for example, we can see that in cluster 1, this cluster is characterized by a lower exposure to air pollution, a lower exposure to different variables of the built environment, higher proximity to green spaces, and lower exposure to traffic and noise. On the other hand, for example, the cluster 3 is characterized by different urban exposome during pregnancy and childhood. So, for example, we observe that the children enrolled in this cluster had high exposure to air pollution during pregnancy, but lower exposure to air pollution during childhood. And it's quite the same with the other exposures. And the most interesting clusters are the cluster 5 and cluster 6, which are characterized by higher exposure to air pollution. When I say higher exposure to, I'm comparing this with the overall mean of the study population. So in cluster 5, this cluster is characterized by a higher level of exposure than the whole study population, and also higher exposure to traffic and noise. And cluster 6 is also characterized by higher air pollution, but lower than cluster 5, and also with higher exposure to different variables of the built environment. And what we found is that when we use this cluster variable in a linear regression, for example, we obtain that children enrolled in cluster 5 and cluster 6 show significantly higher blood pressure than the children enrolled in the cluster 1. So with this study, we use 3 different statistical approaches, but with what these methods had different aims and also different advantage and limitation. So first, with the ExWAS analysis, we can provide estimate for each exposure in association with our outcome. And this method, it's easy to implement. It's easy also to compare with a single exposure paper, for example. This method also have a high sensitivity and allow a complete reporting of all the association of our study. At the opposite, there is a quite high fault discovery rate, and we did not consider co-exposure in the model, so some confounding by co-exposure can remain, and we did not test the interaction. With the variable selection technique, so as I said previously, the aim is to identify a set of exposures that predict at best the outcome. So here the advantage is that we obtain estimates that are adjusted for co-exposures. This method shows a lower fault discovery rate than the ExWAS, and we have the possibility to test the interaction. I said that we have the possibility because I did not look at this interaction using the DSA, but just to let you know that this is a possibility with this method. But some limitation of variable selection are, for me, this is the main limitation is that these methods are predictive methods. That means that the aim of this method is to predict your outcome and not to make or to find which exposure are truly associated with your outcome. For example, if we have, for example, five variable or 5 PCB. I hope everyone knows what are PCB. PCB are chemical compound that were exposed mainly through diet, and they are highly correlated. So when we look, when we use a variable selection technique and we put all these 5 PCB in our model, which are highly correlated, even if they are lower than 0.8, the algorithm will select one of these 5 PCB and will consider that taking into account one PCB is enough to predict the outcome. So it will not include the 4 other PCB, but that doesn't mean that these other PCB are not associated with the outcome. So I think this is... Sorry, someone has the mic open. Okay. Yeah, sorry. So yeah, when you want to translate your result to people that are not familiar with this technique, you have to take care that people did not misunderstood that means that the other 4 PCB are not associated with the outcome, which is not true. Another issue of this techniques is that you can have some difficulty to manage missing data. And we have to find some strategy to take into account, for example, the multiple imputed data set if you have done multiple imputation. So for example, for the DSA, what we have to do is to take all the imputed data set and then to weight the individuals, to take into account that these are not different individuals, but the same individual, including different imputed data set. And then another limitation that we have to take into account is the computational resources that these techniques ask. And finally, for the clustering, so this aim to identify subjects that share similar exposure patterns, and it allows us to identify some subpopulations that are at risk, for example. And the result of these techniques may have good sorry, I missed my word. Could be useful for intervention study, I guess, because, for example, in this study with the blood pressure, what we are able to do is to visualize the location of all study subjects in a map. So, for example, in this study, we include some children from Sabadell, so a town in Catalonia. And we are able to visualize where the children enrolled in cluster 5 and cluster 6 are located. And I think this is an easy way to translate our result to policymakers, or to identify where the issue or the risk can be located in a city. However, this technique also have some limitation. So in the interpretation, we cannot identify which exposure is the main risk factor, for example, since we are looking at all the exposure together. We also have a loss of information, and as for variable selection, the management of missing data could be an issue. So in ELIX, we made a step forward compared to previous single exposure study, but some statistical issues remain, especially to test some interaction between exposures. So a simulation study similar to the one I showed you previously was done to compare different methods to test interaction. And the main conclusion of this study is that the DSA also performed well to test interaction. Another issue that remain is the non-linearity association between exposure and outcome that we did not test in the ELIX protocol. And also the fact that we may have differential measurement error because we are including a lot of exposures from different domains. For example, we will not have the same measurement error when we use biomarkers of exposure than when we use GIS assessment of air pollution, for example. So here the idea is to improve the accuracy of this measurement. So for example, in athlete, we plan to collect repeated urine sample to decrease the measurement error for biomarkers of exposure. And another possibility is to use a statistical model to correct for this measurement error. What we also want to do in athlete is now to take into account the causal structure of the exposome. So for example, if we think about air pollution and green spaces, we know that green spaces can improve or decrease the level of air pollution. But in the analysis we did not consider this association between different exposures. So it could be also the same between exploring the association of diet from one hand, and on the other hand, studying the association of biomarkers of exposure with the outcome, but knowing that these biomarkers or these chemicals came from diet. So the idea now is to take into account this relation between all the exposure. And since we will be collecting new data in athletes, we also need new statistical techniques to deal with repeated data, either repeated exposure or repeated outcome. So these are the main objective of work package 3 of athlete. So I think we can have a small break, or I can do a small break. And if you have any question, Amanda, if you see...
Yeah, no questions so far on the chat.
Good. So this...
yes, yeah, we have a big one here. Okay. From Hector. Hector, I invite you to open your mic, maybe, no?
Yeah, hi, thank you. Yeah, I've been saving it up for when with the moment arose. So, well, 2 questions really. So one, so when we've done lots of classification work in the past, we've always been very careful to always try and do lots of resampling of the data, on the actual data being analysed, rather than on doing the resampling on some theoretical data set, pick a method and then apply that to the real data, And the reason would be, particularly when we're using things like a prior PCA step before a regression, right? Because you're worried about the stability of that PCA model. You're worried about overfitting of your model to that particular instance of the PCA. And are you really assessing the sort of level of bias and overfitting of the model, say when you're doing variable selection on a particular set you've just happened to select, So we always like to see the sort of null distribution of that. I don't see that happen so often in the exposome work, and I wonder if you can comment why. And I guess related to that, when you do see these clusters, and I agree that they're important to understand, when I look at other fields, they tend to become more meaningful as you see them repeat the same clusters repeatedly in multiple data sets. And again, is that something we can address in exposure work?
Yeah, I totally agree with you. For the classification and the PCA, it's true that we we have to repeat the findings. And I'm just thinking that maybe we can also just split the data set, like the training and validating data set, maybe, I don't know. And for the variable selection, we saw that there is some issue with the stability of the selection, and I did not precise this today, but what we did is to repeat the algorithm 100 of times and to include in a regression linear model only the ones that were selected in sufficient percentage of this selection.
Right.
Yeah. And this is also what we recommend for other techniques, such as, I don't know, if you want to apply a lasso selection in multiple imputed data set, for example, you can apply this in each data set and then try to combine and to only consider as truly associated the ones that were picked up in these different
for lasso we found that particularly necessary. So I think it's good to hear that you agree with that point, that your experience matches with ours. Okay, thank you.
I totally agree. One, in ELIX project, have you split your analysis by cohort and observe the consistency between cohorts? So in ELIX, we first pulled all the cohorts together, and then we explore this association, for example, the one that were selected by the DSA. We test this exposure using a meta-analysis. And so exploring the association between each cohort. So in some case, we see that the association are quite similar in each cohort. But for some other exposure, we observe the opposite. And I realized that I talk about an association with temperature during pregnancy and diastolic blood pressure in the example I provide. And this is, for example, this is an example of heterogeneity between cohorts. Since at the end, when we perform this analysis, looking at the association between temperature during pregnancy and blood pressure in each cohort separately, we observed that this association was driven by one cohort. So at the end in the paper, we did not put a lot of emphasis on this result because it was driven by one cohort. Is there any question? What time is it? Okay. So if not, I will continue. So now I will talk about the data pre-processing. We have to, one more comment.
Yeah, for actor again.
Cohort differences can also drive correlation structure which impact cluster analysis and dimensional reduction. Yeah, you are right. Also, I did not precise all the pre-processing, the data pre-processing we made. For the cluster analysis, what we did is that we, and the PCA, we performed two different analyses, one using the exposure variable as they were in each cohort, and another one after standardization of the exposure within each cities. So we try to remove the cohort effect and potentially the correlation between, oh no, not sure if we can remove the, no, I think it will not impact the correlation within each cohort, but we try to remove the cohort effect by standardizing all the exposure on the cohort or the city of inclusion. So if there is no more question, we will continue with data pre-processing. If I can move, okay. So, sorry, is there someone who wants to speak? No, okay. So, when we collected data for an exposome analysis, we collected a very high number of exposure data, and we have to do some steps before trying to study this exposure in association with the health outcomes. So this is the different steps that we perform in ELIX. And I guess this can be applied to any other project looking at exposome health outcome association. So the first step was to exclude the variable with a high missing rate. So we consider that there are not enough information using this exposure variable to include in the analysis. So we exclude the exposure variable, which have more than 70% of missing in the whole study population, and also all the variables that were missing in more than 2 cohorts. So at that step, you can remove some exposure from your data set. And then you have to impute the value below the limit of detection in case you are studying some biomarkers exposure. And you can, for example, use a distribution-based imputation methods, or you can also consider to categorize these exposure variables if the detection rate is too small. And you can also do this step after the next step, which are the variable transformation. So here we suggest to transform your variable for two different reasons. The first one is to improve the imputation process that we are doing just after, because some techniques need to be applied on normally distributed variables. And this will also reduce the influence of the extreme values on some data. If you have, for example, a log normal distribution, applying a log transformation will allow you to decrease the influence of these high values. Or you can also consider categorizing the variable if you cannot achieve normal distribution. And then you probably have to impute the missing data, because as I said previously, as the number of exposure increase, the number of individuals with no missing data decrease. So you have to impute the missing data of your exposure. I do not recommend you to impute the missing data on outcome. And the number of imputed data set will depend on your sample size and the missing rate of your exposome dataset. So in ELIX, in the subcohort that include 1,300 individuals, we imputed 20 datasets. And then to improve the comparison between the estimates, I recommend you to standardize all the exposure variables. So in ELIX, we standardize all exposure by interquartile range. So this will allow us to compare the strength of the estimate between different exposure domains. And then you may consider to perform a priori selection of exposure to reduce more the dimension of your data. So for example, in ELIX, we have removed the exposure that were highly correlated with another. So for example, for air pollution, if I remember well, the NO2 and NOx are highly correlated, and this may lead to some issue in the multi-exposure model. So we decide to keep only one of these two exposures. And we also decide to select only one exposure within a group of exposures that measure more or less the same things. For example, for green spaces, we assess proximity to green spaces using a different buffer. So at 100 meters, 300 meters, and 500 meters. So we decide to only include the 300 meters in the main analysis. And also, if you have some variable available at different time point, and that, yeah, you may want to look at the longitudinal effect, but if not, you can only pick up one. So, for example, for various exposure, they were assessed either during the whole pregnancy, but they are also available by trimester of pregnancy. So instead of include all these variables in the multi-exposure model on the variable selection step, we only select the exposure assessed for the whole pregnancy. And you may have also some variables in continuous and the same variable that you have categorized. So you can select only one of these two. And I think my main recommendation is to automate your script, because when you are dealing with hundreds of exposure, if you have to check the I don't know, the distribution of each exposure, then to standardize each exposure, etc., you will spend a lot of time doing that. So automate your scripts. This is, I think, the best advice I can tell you. And to do so, what we did in ELIX is that we created an Excel file listing all the exposure, but also the covariates that we collect in the project, and we put all the useful information for us to manage all the analysis. So, for example, in this file, we can have obviously the name of the variable, to which family it is related, if it's an exposure or covariates or an outcome, the time window, the type of variable, if continuous or factors, the missing rate, the transformation we used, a subset of pre-selected variables, and also you can use a column to define some labels that you can use then in the plot. And this file will help you you can use this file as a filter for data manipulation. So for example, when you want to test the normality of exposure variable, you can say that within this descriptive file, I want to keep only the variable category, which are exposure, and the type of variable, which are continuous. So for example, this is a screenshot of the ELIX description file. So we have more than 500 rows and 35 columns. And you can see that, for example, here we have the category of exposure. So the category of variables, sorry. So these are exposure variables measured during pregnancy. They are part of the external environment, and they all are from the air pollution family. Then we have some subgroup. For example, NO2, here we have different variables because they were measured at the first trimester, the second trimester, or the third trimester. We have the transformation used, the offset, I will talk about this later. And here, if this variable is part of the pre-selection of exposure. So this is a very huge file, but I think it is very useful to have it for various reasons, because you want always to check, okay, what this variable is exactly, because when you have 200 variables, you may not remember all the name of all the exposure. So it's very useful to have this kind of file. And concerning the data set that you can use to explore exposome-health outcome association. So there are different type, I can say. So you can use the original data set, so before imputation, to make some descriptive statistic, but you can also perform an ExWAS analysis before imputation. You can have multiple imputed data sets, so you can also, why not, make some descriptive statistic, an ExWAS, and variable selection. And here, depending on the method you want to use, you may use a stacked data set with all the imputed data set in a single data frame, or you can maybe try to perform the analysis in each imputed data set separately. And you can also have a third type of data set, which is a single imputed data set. Or if you are lucky and you don't have any missing data, you may use a complete case analysis. And here you can do whatever you want. Descriptive statistic, ExWAS variable selection, data reduction, clustering. But you have to know that this is a single imputed data set, so it may not be accurate to really capture the impute well the missing data. So I think we can have another small break if there is any comment.
You have a question from Nathalie.
In the case where exposome include continuous and categorical variables, how do you standardize categorical variable before including them, and how the type of variable impact its probability to be selected? So for the categorical variable, we do not standardize them. We keep them as categorical. And I'm also wondering what can be the impact on the probability to be selected in the variable selection technique. And I don't know. It would be interesting to test this. What I can say is that, for example, with the DSA, it's a bit not frustrating, but the fact is that if you have a categorical variable with more than 2 categories, the DSA will convert these variables in dummy variables. And then the DSA can select only one categorical, one category of this variable. And it's a bit tricky to know at the end if we have to consider the whole variable or only this dummy variable. And I think this is a point that we still not have any good recommendation to manage the categorical variables. And also for the PCA and the clustering, we exclude all the categorical variables. But we may apply other type of I missed the word in English. Other data reduction technique that can manage both categorical and continuous variable. Any other question? How do you include categorical? Yeah, we exclude the categorical variable in the PCA. And question from Yuan: with which value do you impute a value below the LOD? If you have a lot of value below LOD and impute 0, you will be troubled to use log transformation to correct for the normality. Exactly. So I think the imputation of value below the LOD depends on the detection rate. I mean, if you have only 5% of value below the LOD, you can just substitute the missing, which are not really missing, but the value below the LOD by LOD divided by the root square of 2, for example. But when you have more value below the limit of detection, for example, I don't know, 30% of value below the limit of detection, or 50%. Here, I recommend you to use distribution-based imputation method. So that means that first, you will estimate what is a true distribution, knowing that you miss some value because they are below a defined value, so below the LOD. So in that step, you first need to define this distribution, And then you can randomly select it, some value between 0 and the LOD that you can simulate it, and imputed your value below the LOD by randomly selected value between this estimated distribution. So I will not recommend you to substitute the LOD by 0, and when you are a step forward, because I will talk about this log transformation of 0 value just after, because as you may know, the log of 0 doesn't exist. So this is why one is asking this, I guess. So we will have an offset, but we will talk of this about this later.
There is one more question, but two. One from Daniela. Yes.
So when you perform multiple imputation and different variables are selected in the imputed data set, how do you combine the estimate of variable include in some imputed data set and exclude in other one? Okay, so I hope I understand the question. So what we did in general is that we first perform the variable selection. So in that case, you can do a first variable selection in the first imputed data set. So we will have, I don't know, 3 variables selected. You do the same in the second imputed data set. You will have 5 selected variables, and so on. And then you look which are the variables that are selected in, I don't know, all the imputed data set or in 50% of the imputed data set. And then you will apply classical regression. So I don't know, a linear regression, adjusting for this variable. And then, so using the imputed data set, and then you will combine the estimate using the Rubin's rules. So I don't know if I answer well your question, and if
Daniela, could you open your microphone, and so you can discuss?
No, I mean, for the excluded variable in some imputed data set, then you however consider them in the final model.
The excluded variable?
I mean, because you have a different selection in each imputed data set, no?
Yeah.
Then for some variable, the effect is not estimated in the imputed data set. So when you combine the total estimate, how do you consider those variables? You are including them, however, and you combine only the estimated coefficient for those variables in the imputed data set for which you have those variables?
I'm not sure.
I mean, for the variable not selected in some imputed data set, you have a coefficient equal to 0.
Yeah, but this is what I said, that we do this in 2 steps. So first, we run the variable selection, and then we perform a linear regression, for example, with the variable that were selected. So we are not using the estimate of the coefficient given by the variable selection methods, but we are applying classical linear regression, including all these selected variables in a separate model. So here we can pull the estimate of the coefficient. But I know this is some discussion that we have about interpreting the coefficient provided by the variable selection techniques or not, because it's true that the aim of this variable selection technique is also to consider the correlation between other exposure and to shrink the coefficient. So we know that this will not be taken into account if we apply a classical linear regression and if we include two correlated variables in this linear regression. So this is not totally perfect, I have to say, but this is...
It's difficult, it's difficult.
Yeah,
okay, thank you. I want to understand what's doing. Thank you very much.
You're welcome. And a comment from Hector. We have used frontal regression, imputation of loss sensor data in the past. Yeah, this is a good method to include the value below the LOD.
Hi, Gabrielle, could you open your microphone maybe? Okay, he put the question in it.
So in the single exposure approach, it's multivariate linear regression. I mean that you can adjust for any covariates, but you only include one exposure of interest. I will take the advantage of this question to raise another limitation, is that with the ExWAS analysis, one issue that we fix the set of covariates in our model. While we know that, I don't know, if you are studying air pollution, we may not want to adjust for the same covariate as when you are studying exposure to chemicals. So this is one limitation of the ExWAS, is that to date, we define a set of covariates which is common to all the exposure of interest. So I guess I answer to Gabrielle. What time is it? 11:30.
Or is just put you want single exposure? Gabrielle, are you trying to answer your question?
You include one single exposure. Yeah, for the ExWAS, we look at each exposure separately. So we create as many regression we need to look at all the exposures. So we make one model to study, I don't know, PM2.5, and then another model to study PM10, then another model studying exposure to PCB, another model to a pesticide, and so on. And all of them are adjusted for the same set of covariates. An invariable selection approach, is it a multivariate linear regression? Yeah, it's also a multivariate linear regression. So we adjust the model with the same set of covariates than in the ExWAS. Any other question before we move to our exposome? Okay, I will continue, but if you have any question, you can write them in the chat. I hope we will have time to talk a bit more. One more.
Yeah.
Big one? No. The exposure variable measured at different time points are not there pretty correlated. Why do you include it? Yeah, this is why we. So in the ExWAS approach, since we don't care that the variables are correlated because we are doing separate analysis, we study all these time points in the ExWAS analysis. So we have one model for the world pregnancy, one model for the first trimester, one model for the second trimester, and so on. However, for the multi-exposure model, so for the variable selection, we make a pre-selection of exposure. This is what I was explaining before. So we decide to only consider the variable corresponding to the world pregnancy, and we did not include the variable estimated by trimester of pregnancy as potential candidate for these models. So we did not include this highly correlated exposure as potential candidate for the variable selection models. And this is why in the example I gave for urban environment and blood pressure, I said that I don't know why I don't move my slide. I have them. Yeah, here. So this is why in the ExWAS we have 150 exposure because we include all the time points. But for the variable selection, we have only 67 exposure because we remove the different time points and some other exposures that were highly correlated. So I think I answer your question. And what about the same exposure at pregnancy and at 4 years old, for example? So for the variable selection, we include both the pregnancy and the 4-year periods, except if they were correlated at more than 0.8. But I think it did not happen in our data set. So I will continue with the rexposome package. So just so the rexposome package is a R package developed to enable comprehensive analysis of the exposome and its association with human health. So this is a package developed by IS Global researchers. So one Ramon Gonzalez and Carles Hernandez created this wonderful package, and Xavier is now continuing doing some update on the package. So this package incorporates different tools. So you can make some data visualization. You can apply an ExWAS, PCA, hierarchical clustering, and also ElasticNet. And most all these functions work with a single data set. And some of them can be applied with missing data, but you have to know that if you have missing data in your analysis, this will lead to the exclusion of the participant in the analysis. And some other methods, so the PCA, the clustering, and the ElasticNet can only be applied using complete case analysis, so without any missing data. So this is a brief table to show you what kind of data you can manage with the different methods. So with a single data set, you can do everything. If you have some missing data, you can only perform data visualization and ExWAS. And if you have a multiple imputed data set, you can only apply the ExWAS. So the data structure is a bit important to use our exposome. So the first step you have to do is to create what we call an exposome set object. And this exposome set is composed of 3 different files. So you have a description file, which is the file I showed you previously with all the variable name, the transformation used, the family of exposure, and so on. Then you have a data set with all your exposure variables and a third data set with your outcome and covariates. And an important thing to know is that all the exposure that I include in your exposure file, so the code name of your exposure file, must match with the variable you have included in the description file. And same for the individual, the identifier of your subject must match between the exposure and the phenotype file. So this is something that you need to do before starting to use rexposome. And then if you want to use this, the rexposome using multiple imputed data sets, you only need two different files. So the description file, which is the same as previously, and your imputed data using a state data set. So you have first the non-imputed data, and just below the first imputed data, and so on until you reach the whole imputed data set. And you must have these two variables, which are the .imp and .id, which identify to which imputation data set this each row is related. So then when you create your exposome set object, you can, for example, plot the missing distribution. So here we can see that there are very few missing on air pollution, a bit more missing for PCB, here for metals and phthalates, and brominated compound have quite a lot of missings. So you can here just visualize the repartition of the distribution of missings in each exposure. You can also plot the correlation between all these exposure, taking into account the family of exposure on which that depends. So we have one color for each family, and the color of the line between two exposure represent the correlation between this exposure. Or you can also have another tools to visualize this correlation. So here we can see that the air pollutants are highly correlated. Here we can see another group, which are the organochlorine compound, polybrominated, and here the phthalates. So these are some functions that you can use to visualize the correlation between your exposure. You can also see the distribution using some box plot. So on the left, it's a box plot using a single data set. So you have the distribution of each phthalate here. And on the right, this is the box plot you obtain when you use multiple imputed data sets. So here we have, for example, the distribution of the PFOA in the non-imputed data set, in the first imputed data set, so 1, 3, 4, and 5. So you can see that the imputation did not change a lot the distribution compared to the non-imputed data set. So then when you want to look at the association between the exposome and the health outcome, you can use the ExWAS function. So here a regression is performed for each exposure independently, and you will obtain the estimate, the 95% the confidence interval, the p-value. And there is a function called TEF for threshold for effective number of tests, which is a method we implemented in the rexposome package to correct for multiple testing. So it is similar to a Bonferroni correction. The only difference is that instead of dividing, so the Bonferroni correction for multiple testing, it's you take the value of alpha, so usually 0.05, divided by the number of tests you perform. So if you have 100 exposure, you will divide 0.05 by 100, and obtain a new threshold to interpret your association. So with the method we use in our exposome, what we did is to take into account that when we have a lot of, no, not a lot of, but when we have highly correlated exposure, these tests are not totally independent because of this high correlation. So instead of divided the 0.05 value by 100, we will divide it by a smaller number defined according to the correlation structure of your data. So for example, we will move from 100 to 75 tests. So we will divide 0.05 by 75. And we will have a new threshold to interpret the result. But this is something which is included in the exposome package. You don't have to calculate it by your own. And as I said, the ExWAS function is available for both exposome set or imp exposome set object, so single data set or multiple impute data sets. And the estimates are pulled using the Rubin's rules. So then when you apply the ExWAS function, you can also visualize the associations. So here is the Manhattan plot, when you can see in the x-axis, the p-value of the association, and in the y-axis, all the exposure. And you have different colors depending on the exposure family. And this red line is the threshold of the correlated p-value. So here we see that most, I think it's air pollution. So different variables coming from the air pollution family are associated to blood pressure in that case. You can also use the plot effect to plot a forest plot. So with the estimate and its confidence intervals, and a volcano plot. So sorry, the color are quite light, but each dot corresponds to one exposure. So you have here the p-value, the coefficient, and here the p-value. So, and this line is also the threshold after correction for multiple testing. So you can see, I do not put the name, sorry, but we can do it. This variable cross the p-value, the corrected p-value threshold. So we can also apply principal component analysis using the PCA function. So this is only done using continuous exposure and need a standardization of the exposure variables. So we obtain different plots. So here we have the exposure projected on the first and the second components. Here are the individuals, the explained variance, and the cumulative explained variance. We will see this again later. You can also see the correlation between each exposure and the principal component, and the association between the variables that are included in your phenotype files, so the outcome and potentially the covariates, against the principal components. So here we can detect that there's probably an association between the first principal component and blood pressure and maybe rhinitis. But this is really for visual information. And finally, you can also perform a clustering analysis still on continuous exposure, and you can visualize the tree, the classification tree. Okay, so we define 3 groups of individuals, and you can see, depending on the color of the bar, if the variable is, or if the subject have higher or lower exposure than the whole study population. And I think this is the last function included in the rexposome package. I have to acknowledge that I did not use it. So I just try to perform an elastic net analysis to show you that this is possible. And you can see which exposure were selected or considered in the elastic net analysis. And there are also some extension of the rexposome package. So there is the omics rexposome, which is an extension of the rexposome package to perform analysis joining exposome and omic data. There is also a Chinese app that compiled all the functions, including the rexposome and the omic rexposome. And these two packages are also implemented in datasheet, but I have to say that I never tried to use them in datasheet, but they are available.
Charlene, I have a question from Constanza about the PCF function. Doesn't the PCF function automatically standardize the variables?
I don't remember. We will check this just after in the code. We will see easily if it's automatic. So I think so, but not sure.
Okay. And also you have just a comment from Maja about the multiple tests correction using the estimated number of the independent tests seems to be less conservative than Bonferroni. Why I would expect some more conservative procedure given the correlation structure and an increased false discovery rate.
Yeah, I think we can have a lot of discussion between this and for me.
Maja, where are you? If you want, you can open your microphone too. I don't know if you have time.
Not a lot.
Yeah.
But no, it's for me the Bonferroni correction. It's the more conservative method that exists, and I think we are decreasing a lot the sensitivity when using the Bonferroni correction, and this threshold for the effective number of tests, it's a good compromise to not be as conservative as Bonferroni is. But you can also, there are plenty of methods to correct for multiple testing, like the false discovery rate. And yeah, I think we can talk during hours about the correction for multiple testing. And
yeah, because usually when you have like very correlated data structure, the golden rule is to use the permutation procedure to estimate the null distribution. So I think that would be the most appropriate approach, although it's very computationally extensive, so it could be the problem. Yeah, because I think that by correcting for the number of independent tests, you don't resolve the problem of the quite high false discovery rate.
No, the false discovery rate remain high even whatever the correction we apply with the ExWAS methods. Yeah. And this is why we recommend to not only perform an ExWAS, but to explore other methods and to provide an overview of the result using different methods that are maybe complementary and a good compromise between high sensitivity obtained with this ExWAS and low false discovery rate with variable selection. So
yeah, but in this package, you all do you have different options for multiple testing correction, or only this one?
I think it's only this one, but the rexposome is still
Developing.
yeah. So if you think this is very important, and I agree with you that we would be able to choose which kind of multiple testing correction we would like to implement. So I can talk with the package developers to see with them if there is any possibility to add other methods.
Okay, thanks.
So this was my last slide, I think. So just to give you some useful resources to use our exposome, where there are I think I can try the vignette where you can okay. So this kind of web page where you can see all the function and how you can apply them and so on. So now how can I go back like that? And also the same for the Shiny app and the Omeka rexposome. And that's it. If you have any other question, we still have time. And then I would like to show you in practice how you can do this kind of analysis with R. And I don't know if all of you, if all of you can see the chat. So at the beginning of the session, I just
I have just put it again, Charlene, the link for the R script.
So following this link, you can find the R script that I'm going to use, and you will be able to execute it if you have RStudio open and if you manage to install R exposome. So if there is no more question, I think I will move to R. Okay, so in this script, I give you just the few lines of code to install the R exposome. So these are the same line I sent to you on Monday, I guess. I think, sorry. So after loading the R exposome package, you can just following this line to locate the file that are already included in the R exposome package. So you after the installation of the R exposome package, you can find this this file in the folder where the exposome is, the R exposome package is installed. So I'm just loading them. And so we have our three different files, the descriptive file. So we have one column for the family of exposure, one column with exposure name. Yeah, the code name is not very meaningful, but these are the exposure name and the label of the exposure. In the second file, so the exposure file, we have our identifier and all the exposures. So we have 109 individual and 88 exposure variables. And in the phenotype files, we have some outcomes, so some respiratory outcome and some covariate sex, age, BMI, or blood pressure as an outcome. So we just need to convert the categorical variable as the factors. So this is quite easy. And just for the illustration today, I just need to transform some variable which were already transformed. So I'm just back transform them. So this is just for today for the exercise. So yeah, I already show you that in the descriptive file we have 88 exposure, as in the exposure data, and the phenotype include 9 variables with 109 individuals. Yeah. So then, as I said, we have to manage the row names. So the row name of the descriptive file must match with the code names of the exposure files. So we just apply some row name change. So this data set is not imputed, and we will now import it in exposome, so using the load exposome function. So here we are in the case of a single data set that we want to include in our exposome. So we are now created an exposome set object, which is called exp, and we can see the name of the sample, the name of the exposures, the family of exposures, and the phenotype data. And you can also access to this exp object. Using the expo, you can have access to the exposure, so which at the end is the same data as the one you import before using the EE data preprocess. So we have missing data. They are not totally missing, and we have some data. We can also just look at a subset of exposure. And you can also perform some summary statistics. So here, for example, if we want to have the summary of the PFOA, we can have the median, the quartile, and so on. You can also plot the histogram of this variable. So these are some functions that you can use for descriptive purpose. And then using the plot missing function, you can have the figures I showed you before with the distribution of missing for each variables. You can also have this as a table of the number of missing or percentage of missing for each variable. So here we see that there is 69% of missing data for the BD99. And in the data preprocessing part, we said that in ELIX, for example, we exclude the data with more than 0.7, so more than 70% of missing. So here it's okay. We don't have any variable with more than 70% of missing. We can use a plot family function to have the box plot for each phthalate here, because I just ask a subset of phthalate, but we can also use another family. And you can also perform this plot using a grouping variable. So here, for example, the sex. So we can just see the distribution of each phthalates depending on the sex of the individual. And you can also plot all the family together. I will not do it because sometimes in my computer it is crashing. So I don't want to have a crash now, but you can do it. And then using the correlation function, we can create the correlation matrix. So there is some warning because to calculate this correlation matrix, we are also trying to find a summary statistic to define the association between categorical variables. So this warning came because of the chi-square test used to compare the association between two categorical variables. So don't worry about this. And here we have the correlation matrix for all exposure. So, and this correlation matrix is used to plot the correlation. So the two type of plot I showed you before. Okay, if okay. So in circle or in matrix. And then you can also perform some normality test within rexposome. So you can use the normality test function and see how many variables are normally distributed or not. So here only 21 are normally distributed. You can select the ones that are not normally distributed. You can also plot the histogram of a specific exposure using different transformation. However, here I recommend you to perform all these steps of variable distribution, variable transformation, and imputation outside the rexposome package because it's easier to manage and you will have more flexibility also to test additional transformations that are not implemented in rexposome, for example. Because here, only 3 types of transformation are applied, which is an exponential transformation, a log transformation, and a square root transformation. So, and there is also an issue with the 0 value. So I think it's, I don't remember the name, Wuhan, Wu1, I like
U1.
U1, thank you. I like this issue with the log of 0 that doesn't exist. So even if you have some function in rexposome to do this, I will recommend you to do it outside rexposome. So from here, we exit rexposome, and I providing you some function to automate the transformation and this is mainly for the transformation of variables. So I just give you some function that we use in Helix. So this function is to determine the best value to add to a variable that we want to log transform to obtain the best Q-ness, so which is a measure of the symmetry of your distribution. So we just need to execute this function. We don't really need to totally understand what we are doing this, but if you want, I will explain you, but I think we are running out of time in a few minutes, so I will keep it. This is also another function to apply different transformation on your variables. So as a log, log2, square root, cubic, no. Yeah, this is a cubic one. No, the cubic one is one here, a square transformation with the specific case of the log transformation. So we just check here if we have any 0 value in the variable. So if not, we can just do this. But in case we have some 0 value in the original variable, we just apply this function available here to find an offset to add to the distribution. So this is a function, I'm just logging it. And now if something, I just take. And then you can apply this loop to the exposome dataset, and only for the numerical variable. And what I recommend you is either to have an Excel file on another screen or on a part of the screen where you will fill this file with the transformation you want to use, or to directly create a transformation variable in the descriptive file and say, okay, so this, and this variable, I don't want to transform them. This variable, I want to apply a square transformation. This one, I want to apply a log2 transformation, and so on. So when you apply this loop, I forget to load this. Okay, so now you have, you are applying or visualizing the distribution after different transformation on the variable PFHXS. So this is the original distribution. This is the one after log transformation, log2 transformation, square root, and so on. So if you have your Excel file close to you, you can just add, okay, the PFHXS, I want to choose a log2 transformation. Or you can just add here the PFHXS that I will apply a log2 transformation. And then you press enter and you will move to the next exposure, so here PFOA. So I don't know, we can say, okay, we will also use a log2 transformation, the next exposure, and so on. So we have more than 80 variables. We will not do it for all of them, but we will assume that these are the transformation we want to use. So here we are just filling the description file. So now we have a new column saying that the PFHXS will be log2 transform, and so on. So I did not fill in all the cells, but this is only for the demo. In real case, you have to do it for all the exposure. And then when we have this transformation defined, we can now just apply them to the data set. So just to keep some tracking, I'm just creating a new exposure data set that I called EE-trans or transformation. And then I applied this loop that will look if the exposure in the exposure file is included in the descriptive file. So this is just to make sure that we are not applying this transformation for other covariates or outcome. And then we will ask the descriptive file which transformation is provided in the transformation column. So if it's a log transformation, then we apply the log transformation on this variable and so on, log2, square root, etc., etc. So here, by doing this, we just have created the EE-trans dataset after transformation of all the exposures. But we may have seen that for some exposure, a transformation is not better than no transformation. So we may want to categorize them. So here, for example, the DDT, sorry, I would like to go back. Ah, sorry. Oh. Okay, just to have only one plot. So here, for example, the DDT, we decide to categorize it. So we can see the distribution. We decide to categorize it using the median. We just check that the categorization it's okay. The one in the classified as 0 are lower value than the one classified as 1, so all it's fine. And then we just have to update the exposure and the descriptive file. So here we remove the continuous DDT variables and we change the row name and the name of the descriptive file. So yeah, I recommend you to check again the distribution of each exposure using a loop, for example, to verify that you have the same number of missing before and after the transformation, just to check that you did not do anything wrong. And for this tutorial, we will consider that all the variables are normally distributed, which is really not the case. It's just to play with some data. So we will not make any scientific conclusion with this data set. So now that we have applied the transformation on all exposure, we are ready to implement the multiple imputation. What time is it? I think I will go quickly. So we can merge the phenotype with the exposure data and remove the row name. We will create a predictive, forget to load the library. So we will create a predictors matrix. So here we forced some predictors, including our outcome and some covariates. So for all missing exposure, we want to use these 4 variables as predictors. And in the predictor function, then you have for each line, for example, if we took the PFHXS line, the predictors that were used to fill in the missing value are this one, so the one that we forced, and probably other one later. So here, HEB, BTHH, and so on. We can check that we don't have more than 25 predictors, which is a rule that must be followed. In that case, we have 2 variables with more than 25 predictors. You can check which are these predictors and remove some of them. We check again that we don't have more than 25 predictors, and this is okay. We transform it as a matrix. We can implement a first imputation, but without any iteration, just to check that the methods are correct. And then here we apply that imputation for 5 imputed data set. So this will not take a lot of time. And then you can extract the result of this imputation in a long format. So here you have all the imputed data set state. So when .amp equals 0. These are the non-imputed one, the first imputed data set, and so on. And we will use this data set in long format for our exposome using multiple imputed data set. We check that there is no missing. We can extract the first imputed data set. And we will apply the Acura scaling after the imputation, and we will define the median and Acura value from the first imputed data set, and we will apply them to all the imputed data sets. We can check again that there is no missing created. We can store a first imputed data set here, and then we are almost ready to go into our exposome. We just need to split the exposure and phenotype dataset, change again the row names, and now we can load exposome. So here we are using a single imputed dataset. So we can use the same function as earlier. We can run an ExWAS analysis, which is quite fast. And you can check the value of the threshold for effective number of tests, which is 0.001. You can extract the result of the ExWAS. So you can obtain a data frame with the p-value, the estimate, and the confidence intervals. Extract only the ones that are below the threshold for effective number of tests. So here we have 9 variables which are associated with blood pressure. If you want to see the one below 0.05, these are the plots that we already saw before. Oh, forget to load the library. And yeah, this is a small summary of the association we found. I think, what time is it? It's almost finished. So you can then try the other function with the PCA, the clustering. For the PCA, you can, for example, store the result of the PCA and then perform a linear regression using this, the 4 first component, for example. You can do the same with the clustering. This is the code to apply the elastic net function, and this is the same. It's an ExWAS using multiple imputed data sets, so the code is almost the same, but you can only do an ExWAS, but the results are presented in the same way. Yeah, I just would like to show you the Shiny app very quickly. I just need to export the file that we just created. And then this is the Shiny app. So for those of you or other, if you have some colleagues that are not good to write some code, you can use this this app and just make like click, 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 and you will obtain your result for an ExWAS analysis, for example. So just need to load the exposure description and phenotype file. With the table, define the ID, the name of the exposure, the family, select, and then you can use the same function on rexposome. So here we don't have any missing value because we are using the first imputed data set. You can check the normality. You can have some exposure description. You can here make the ExWAS, for example. So if you want to do an ExWAS with blood pressure and we want to adjust for sex and age, and in a few minutes we will have.
Charlene,
Yeah.
Arthur it's asking why it is so important to have normality. I think when you
it's mainly for the imputation part, because in the, for example, the mice function, we need to approach the normality to make the imputation as best as possible, and also to limit the influence of the extreme value. Because if you have some point with very high level of exposure, they may drive the association using a linear regression model. So to remove or to decrease the influence of this subject, you may want to normalize your distribution to decrease the influence of this extreme point. So I think I will stop sharing my screen, except if just to see you again. If I'm able to go back to Zoom. Okay, so yeah, it's already 12:30. I was thinking that in 1 hour, 1 hour and a half, it would be enough, but not. So from my side, I have no problem if you want to make some question. I still have time. So I have no meeting coming just after. So if you have any question, feel free to ask them either in the chat or you can just turn on your microphone. And I hope this tutorial was useful for you and that you will use rexposome in few days or few weeks for your next analysis.